The sun has shaped every form of life on our planet, dictating instinctive responses to the cyclical changes between day and night, between season and season. Yet, when we design the building we spend our days in, most of the time we tend to follow rules and codes that disregard sunlight completely for the sake of simplicity and continuity with the past.
My name is Eleonora and I'm a PhD student at Loughborough University. My work is helping to establish within the design community a holistic way of predicting daylight in spaces that accords with our experience of natural illumination, skylight and sunlight acting together. Climate-based daylight modeling uses data from standard weather files, collected over many years of measurements to represent the typical climate for a specific locale. The constantly changing sun and sky representation derived from this data are inserted in the simulation together with the building model and its material properties. For example, glass transmittance or reflectance for opaque surfaces. The luminous quantities calculated by the simulation engine are typically luminance and illuminance. But to better interpret these results when assessing the luminous performance of a space, it is generally preferred to use annual metrics, such as useful daylight illuminance or daylight autonomy. In fact, these two annual metrics have been adopted as mandatory calculation required for the Priority School Building Programme that the UK Education Funding Agency launched in 2013, setting a precedent for daylighting codes and guidelines worldwide. However, unlike, say, dynamic thermal modeling, CBDM is a product of a small number of enthusiasts, each one using a different approach. My research project aims at assessing the applicability of climate-based daylight modeling for real-world evaluation and to establish quality assurance procedures to help ensure reliability and accuracy of the outputs. At first, I had to understand how practitioners actually employ CBDM, so I conducted some face-to-face interviews with designers at ARU, the research industrial partner, and then through a wider online survey. Next, I'm conducting an intermodal comparison to evaluate the various approaches against a validated benchmark. For this, I modeled the rooms in SketchUp and in Rhino and have run several parametric and sensitivity analyses, focusing on the inputs required by a CBDM evaluation, so weather files, sky models, virtual sensor planes, and material reflectivities. So far, the results show that by using metrics that take into account both direct and diffuse daylight, such as UDI and DA, the different calculation techniques compare remarkably well to each other. However, when the metrics are quantifying only the direct component, for example using annual solar exposure, the differences in how the existing techniques simulate the direct sunlight contribution lead to significant differences in the final results. The following step will be the comparison between the results from the simulation and the real data acquired for another research project carried out by my Loughborough colleague Nafsika Drozo. Our two projects share the same case studies, 4 classrooms chosen within a couple of college and schools in Leicestershire, where she is collecting luminance records via high dynamic range images. While real-world case studies are plenty of confounding factors that make any attempt towards a validation practically impossible, we hope anyway to draw some analogies that could inform us about, first, which of the considered CBDM methods better represent the real luminous performance of the spaces, and second, which of the metrics is a viable indication of user visual comfort. Quantifying how much access to daylight we get while we are inside our schools, our workplaces, our homes, will help creating spaces that actually boost our comfort and well-being.